Okay. Yeah, so what I wanted to explain here is we are trying to figure out the potential for this problem for two cylinders, yeah, inside of each other. And we're trying to figure out the potential difference between a point on the axis and a point on the surface of the green cylinder. Okay? And what I wanted to show you, a bit of the shortcuts that we could use here to evaluate this. Uh, and so, so by definition, the potential is, if we were to find the potential anywhere, V of r, right, would equal negative the integral from some reference point all the way to r e dl. Okay? So the reference point is some standard reference point which we can agree on. Okay? So V depends only on the point R, right? So this is the electric potential. Now, if I were to take 2 points, VA and VB, generally speaking, yeah, well, I could say, according to this, VA, or let's start with VB. VB is equal to negative the integral from some reference to point B e dl, right? And you're with me?
Yeah, it says
Nice one.
the connection was lost.
Right. And by the same exact logic, I could say VA, okay, with those being vectors, is equal minus the integral from the same reference to A of EDL. Now, notice if I were to subtract VB minus VA, what do I get? I would get minus reference to B EDL, minus minus becomes plus, reference to A EDL. Now, this minus sign, I can flip these two bounds here, right?
I
So,
can't see your screen.
oh, you can't. Let
No,
me share it
it
with you
dropped
again.
that. Yeah.
And let me close this team viewer. We don't need it. Okay, so so you could see my screen now. Right? Ben,
Yeah.
you can hear me?
I can hear the screen bubbly and everything. Oh, what I think is to your pad.
You see my pad? Okay, and so if
Yeah.
I subtract them, I will get VB minus VA, and I can switch the bounds here, and this becomes B to reference of EDL plus reference to A of EDL. And of course these two integrals will combine and there's no more reference, so VB minus VA will equal the integral from A to B of EDL. Wait, did I lose a minus sign here somewhere? VB minus let's see, plus, so this is oh yeah, there's a minus because technically this is B to A, but I flipped the bounds, so I need a minus sign here. So this is equation 222 that we need to use. You can't see my screen?
No, just like I see the top of it, but it's just all black.
No, I see that it's still shared.
Yeah, but like I can see like the top of your screen where like the menu is, but I can't see any of the pad. Like it's all just blank.
Try to scroll up and down on it. It will clear up because that's what sometimes happens with me.
Yeah.
Okay? So I wanted to show you basically equation 222. And from here, we could now do the problem. Now you should be able to do this problem here. Okay, so to be able to find the potential difference here, I will sort of use this derivation so I don't have to worry about the reference point. So let's call the axis point 0 to B. So I want the potential difference in this problem between VB minus V0. So I would actually have to do negative the electric field from 0 to B. However, going from 0 to B, the electric field changes, so I would have to split this into two integrals. So this will be minus the integral from 0 to A of the electric field inside the small cylinder from 0 to A inside the red cylinder, plus minus from A to B of EDL, and that is the value of the electric field in the region between A and B. So this is a different electric field than this. And so let's go ahead and evaluate these two electric fields. So the easiest way, I will use Gauss's law. So let me go between 0 and A. So between 0 and A, and that means I'm inside the smaller sphere. Now I know that these two spheres, this is problem 224 by the way, this is relying on 216, so we have the rho on the inner cylinder, so this guy here has a rho on it, volume charge density rho, and there is a surface charge density sigma on the outer one. So there's sigma on this guy here. Okay, so yeah. Okay, fair enough. So then if I do a Gaussian surface inside my small one, let's say my Gaussian surface is here, for example. Okay, and this is S 0 to S. And so by Gauss's law, so I'm trying to get the electric field here. Gauss's law. Stop writing. Okay, so by Gauss's law, I can say E1 dA integral equals Q enclosed over epsilon. Okay, so E1, so this is due to the uniformity of the shape. I can pull E1 outside the integral. And let's say the length of my Gaussian surface is L. So the volume of the cylinder 2 pi S, the radius of my Gaussian surface is S, 2 pi SL equals Q enclosed. So now for Q enclosed, I would have to integrate rho on the volume of the cylinder, so d tau, and this is uniform, so it can come outside the integral. So this is just basically rho times the volume of the cylinder. So then I would get E 2 pi SL equals rho times pi S squared times L, big L. We're using small l. Let's stick to small l. So L over epsilon, and we can cross out some terms here. So we have E1 equaling rho S over 2 epsilon. Rho S over 2 epsilon. So this is the electric field in the green Gaussian surface inside the smaller cylinder. Okay, so that would now enable me to calculate the first part of my integral. Let's go and get E2. So for E2, I need to be in between. In between, that means I will basically, let's draw this. So this is the large one, and the radius here is the radius of the large one is B, and then there's the smaller one inside. And by the way, this has a surface charge density, meaning all the charges on the surface, and this one here is this guy, and this has a volume charge density. And now my Gaussian surface needs to be, so this guy here is A, and now my Gaussian my Gaussian surface needs to be in between. Okay, and this is radius S. So now my S is between A and B. And so Gauss's law, E2 dA equals Q enclosed over epsilon. And so the same argument, if the length of my Gaussian surface is L, so this is 2 pi SL equals, now Q enclosed will be rho d tau, but instead now the volume will be the entire volume of my blue internal cylinder, because I'm enclosing the entire charge. So that's rho times the volume of that cylinder, which is pi a squared instead of s, because now I'm enclosing everything from 0 to a times L. And then here there's no charge because this surface charge density is only on the surface. So between the two cylinders there's no charge over epsilon. This here is small l. Okay, and then if I simplify that, so we will get E2 to be pi with a pi, L with the L. Of course, it's independent of the length of the Gaussian surface. So we will get rho a squared over 2 epsilon s. So this is E2. Okay, and now we can take 1 and 2 and plug them in A. So plug 1 and 2 in A. And so we're going to get VB minus V0 equal minus the integral from 0 to A. Well, we found E1 to be rho s over 2 epsilon s, and dl here, because I'm going in the direction of the radius of the cylinder due to the symmetry, because the electric field on the surface of the cylinder is like that, and it's perpendicular, so dl becomes ds. The dot product gives us a cosine theta, which would be 0, because ds and E are in the same direction, so cosine 0 is 1, so this just becomes ds. And since rho over 2 epsilon is constant, I can pull this outside the integral. So let me do this. Just move them here, and then put the integral here. And this is going from 0 to A. And with the same exact argument, we can do the second integral. So minus E2. E2 turned out to be rho A squared. This is all constants over 2 epsilon. Integral of ds over s from A to B. And now if we carry this out, we get minus rho over 2 epsilon s squared over 2 from 0 to A minus rho A squared over 2 epsilon L and S from A to B. And if we plug in the bounds, so minus rho over 2 epsilon A squared over 2 minus rho A squared over 2 epsilon L and B minus L and A. And if we just simplify this a tiny bit, we get the final result to be VB minus VA minus V0 on the axis equal, let me factor out rho A squared over 2 epsilon, and I have left 1, or with half, yeah, or I could actually factor out a 4 here, and I would get a half, but so 2 left, because oops, no, 1, because that would be, and there's a minus sign here, because then it would be, the first term will get me, I need 1/4, yeah, which is 1/4, plus ln 2, because there's a 4 in the denominator, ln b over a. So this would be the potential difference. That concludes this problem. Please don't forget to rate, subscribe, and comment.